Greetings, guys and girls. Today, I'd like to talk to you guys about how heat is involved in the dissolving process. Right? And over the last few days, we've talked about two things. When two naturally soluble substances mix, what are some things we can do to speed that process up? And we said that increasing the surface area will do that by pulverizing it or crushing it, and heating it will do that, and taking the substance and stirring it to bring fresh solvent will do that. And I was getting all sorts of times from you guys testing that at home. Then we got into, well, what are the characteristics that tell us if two things should dissolve in the first place, right? The things that affect the solubility. And we were talking about like dissolves like in Henry's law with pressure and then the temperature that factored in. And one of the things that we mentioned when we were talking about temperature, right, which was right here, is that generally for a solid and a liquid, as the temp goes up, the solubility goes up. And I said that exceptions can be determined by heat of solution. Right? Most substances, if you're a solid, follow that pattern. Right? Gases generally work the other way. As the temp goes up, the solubility goes down. And we touched on that a little bit, that most substances break down better in the solid because the increased temp helps overcome IFs and lets the water move faster. All right, but what I wanted to dive into was this whole, well, what is heat of solution? And then how does it affect what's going on? All right, so that's what we're talking about with this here. All right, so if we're looking at solution formation, you have to understand that we can have two types of processes whenever a substance is dissolving. It can either be endothermic or it can be exothermic. Endothermic processes require heat for them to dissolve, right? We tend to heat them, they dissolve better, or they're taking in heat from the surroundings when the dissolving happens. Like exothermic heats of solution release heat whenever they dissolve. So the two substances break down, and sometimes it takes in heat, making it colder. Sometimes it releases heat, making it hotter. So when we look at a heat of solution number, which is represented by delta H, which is called enthalpy, it's pretty straightforward. If you see a negative value, the negative on the number indicates the process is exothermic. If you see a positive number, like the NH4NO3 and the KNO3, those mean that those dissolving processes are endothermic. So negative means exothermic and positive means endothermic. So if I take NH4NO3 and I dissolve it in water, it's going to feel cold to the touch because it's endothermic. It's taking heat in from my hand. But the NaOH, or hydrochloric acid, if I put them in water, they would release heat overall, which would feel warm to the touch because I'd have heat entering my hand for the exothermic. So where does this heat come from? Right? It's a good question to look at. And whenever we dissolve a substance, fundamentally it happens in three basic steps. Right? The first step is called expanding the solute. So if I want to break a solid down, I'm going to have to separate it from all the other solid pieces, which are held together by intermolecular forces. Right? So if I want to make this guy break apart, which I'm going to have to do to allow waters to interact with it, I am going to have to spend energy to do that because breaking forces is always endothermic, right? We're overcoming those intermolecular forces. It is going to cost us energy. So that's one thing that has to happen when we dissolve. The solid needs to be pulled apart. Similarly, step two is called expanding the solvent. I also have to separate usually the water molecules from each other, right? If I have my solvent, let's say it's water, we have IFs that hold all our water together as a liquid as well. So those IFs must also be overcome so that this solvent particle has the ability to move in and attack the crystal, so that this solvent particle can go in and attack the crystal and try to form forces with it. So the first step, breaking the solid apart. The second step, breaking the liquid apart. Those are both breaking forces. So steps 1 and 2 are both endothermic. They cost us energy. The third step, though, is where I get to form forces. Once we get those things separated, now new IFs are allowed to form. So now my red solid is forming IFs with my blue solvent and vice versa. And those are newly formed forces. And because they're newly formed forces, that makes them exothermic. All right, so here's the step where we release some energy. Step 1, break apart the solid. Step 2, break apart the liquid. Step 3, the solid and the liquid interact with each other, and I release energy when that happens. So overall, the process can be endo or exothermic based on how strong the forces are in each of those steps. So if here's the 3 steps, separating the solute in step 1, separating the solvent in step 2, and forming the solution in step 3, depending on how strong the forces are that hold things together, compared to how strong the forces are between the newly formed substances, we can get an endo or exothermic process overall. If my solute interactions are sort of weak and my solvent interactions are sort of weak, but my solute solvent interactions are pretty strong, the amount of heat released will be more than the amount of heat it needed to break them up. It'll be exothermic. It'll release that extra heat. But if I have a pretty strong solute and a pretty strong solvent, and that's controlled by their intermolecular forces, I am going to have a pretty decent solvent-solute interaction, but sometimes it won't exceed steps 1 and 2 put together. So the overall process is endothermic. All right, so the strength of intermolecular forces has a big deal to do with whether the dissolving process is warm, exothermic, or cold, endothermic. And this is how you figure that out. We would look at it, draw its picture like we were earlier, and we decide, oh, is it an ionic bond? Or does it have hydrogen bonding? Or is it dipole-dipole? Oh, it only has London dispersion. Things like that. And the weaker those forces are, depending on where they occur in steps, you can predict what that is. Now, we won't get into those types of predictions. I just want you to understand where the heat comes from and why it's not always universally endo or exothermic. Right? So every substance can have its own delta H of solution, its own enthalpy of solution. Right? And we can write an equation for those. For the endothermic processes, we know we need heat for that to occur. Right? So if I take a substance, KNO3, interacting with water to create a solution, which is when they're dissolved, if it's endothermic, we treat heat like it's a reactant. On the other hand, if that process ends up being exothermic, right, the HI interacts with water, it creates a solution, and there's heat given off, we write that as a product. And what happens is this, like any other equation, can be manipulated. If I heat the substance, if the heat's on the left, we cause a shift right from Le Chatelier's, I can make something more soluble by adding heat, which is the general trend for solvents. Right? But if it's exothermic, adding heat will actually make it less soluble. It will shift it back to the left side, and you won't see as much of the solid dissolve. So the strength of the forces determine the location and the amount of heat. Right? So if it's endothermic, heat's on the left, and if these forces need a lot of heat, the numeric value is high. If it's exothermic, the heat is on the right. And depending on how much heat is going to be released, the numeric value for the heat can be high or low. So just remember, endothermic substance, heat on the left, exothermic substance, heat on the right. So that all ties into this idea of solubility, and obviously there's a link to temperature. Right? So what happened was they decided there is a very logical graph that you can generate that shows you these relationships. All right, that we will link the temperature on one axis versus the solubility of it on the other axis. Right? And there's a couple important things, right, that I want you to know about solubility curves. The first is, what is a solubility curve? All right, solubility curves show the link between temperature, which is related to the amount of heat, and the solubility, how well it dissolves, of a substance. When you're looking at a solubility curve, right, there are three things that can be particularly useful. Right, thing number one, right, is what are the labels on the axes? You've got temperature and you've got solubility, but what is the amount of solute? What is the amount of solvent? Those things will affect how you read the curve. Number two, when I look at a set of data, where does that put me on the curve? Am I underneath where the curve goes? Am I touching the curve? Or have I fallen above the curve? Because as you can see, right, those locations tell me what type of solution I have. If I'm under the curve, I'm an unsaturated solution. It means I can dissolve more solid. If I'm on the curve, right, I am a saturated solution. I am maxed out. I'm holding as much solid as that amount of liquid can handle. If my set of points put me above the curve, I am supersaturated, which means I am saturated, the liquid is maxed out, but I have solid sitting in the container as well because there was more in there than the liquid was able to hold. Right? Third thing, right, is what is the direction of the curve, right? Is it an uphill curve? Is it a downhill curve? That tells us if it's endo or exo. For your curves that go uphill, they are endothermic. For your curves that go downhill, they indicate exothermic dissolving. Right? So let's go through each of those and I can show you what questions look like related to each of those important characteristics. All right, first one is the label on the axes. So if you look at this curve that I brought up, right, my x-axis is the temp in Celsius. Each one of these lines represents a different substance. This is Ki's line. Here's NaNO3's line. Here's NH3's line. Here's NH4Cl's line. All right, so those are how you know who you're looking at. Then the grams of solute, which are these guys, per the amount of liquid matters, per 100 grams of water. So when I read this chart, the number I get is if I have 100 grams of water. If I don't, that number changes. Right? So the question's set up like this. First, how much NH4Cl will dissolve in 100 grams of water at 50 degrees Celsius? So the first thing I do is I check, do we have the right amount of water? Said we had 100 grams. Hey, this is 100 grams. It means I can read my graph normally. So then what I do is I find my temperature, 50 degrees. Here's my 50. Then I'm going to trace up at 50 till I hit the substance I care about, which is the ammonium chloride, NH4Cl. Right? So we get at our 50, trace up, trace up, trace up, trace up, trace up. I hit here, and whatever the amount of solid says on the y-axis, that is how much NH4Cl can dissolve at 50 degrees. So I trace over, right? So in 100 grams of water at 50 degrees, I can dissolve 50 grams of NH4Cl. Trace up, trace over. Another one, how much KNO3 will dissolve in 100 grams of water at 50 degrees? And so it looks like I asked the same question, but I change the substance. Still in 100 grams of water. So we're good there. 50 degrees means we go here, but this time I'm tracing up till I hit the KNO3 graph. All right, so I trace. Here's where I hit the KNO3. And if I look over, sure enough, it's going to tell me I can dissolve 80 grams of KNO3 at 50 degrees. If I put less in, I'd be able to dissolve more of the solid. If I put more than 80 grams in, only 80 would dissolve, and the rest would be sitting as a solid at the bottom of the beaker. What if we change the amount of the water? All right, that could be an important factor. So I asked the same question, same temperature, but this time I asked it if we're at 25 grams. How much NH4Cl would dissolve in 25 grams of water at 50? So things are different. This is telling me per 100 grams of water. All right, so I would still go to the 50. I would still trace up to NH4Cl, and I know at 50 degrees, I can hold 50 grams of the NH4Cl in 100 grams of water. I want to know how many grams can I hold if there's only 25. So you set up a proportion. The graph will always tell me how much solid dissolves per the amount that it says, and I change the amount of water. So now I can set that up. So I would just say, all right, the 25 times the 50 divided by the 100, I could dissolve 12.5 grams of the NH4Cl. Some people think of it a different way. Oh, you can dissolve 50 in 100. 25 grams is only a fourth as much water. I can only get as fourth as much of the 50. And you would get the same place. You're setting up a proportion just using a fraction. And that works good whenever it's nice round numbers. But what if it's not? What if we do something like this? How much KNO3 will dissolve in 28 grams of water at 50? All right, so we still go to 50, trace up to the KNO3. I hit it. I know if I have 100 grams of water, 80 grams of KNO3 can dissolve. So 80 can dissolve in 100 grams of water. I want to know how much can dissolve in 28 grams. So even if the numbers aren't nice and round, you set up your proportion, you cross multiply, and you'd figure out that you could hold 22.4 grams of the KNO3 if we only had 28 grams of the water. All right, so that's what I mean when I say the labels on the axes are important. All right, you got to watch out to see, are they changing the amount of solvent that they're using compared to the graph? Right, category 2 questions have to do with this whole location of the curve. Where do I live? On the curve, above the curve, under it. So let's say we're looking at the NaNO3 graph, this guy here. If I give you an amount and a temperature, and it plots a point underneath that curve, let's say I gave you 90 grams of it, and I said, you're at 70 degrees, drops me right here, right? I am under the NaNO3 curve. Right? But if I said, hey, you have 100 grams at 35 degrees, you land right on the line. That's what I mean by on the curve. That's a saturated. And then above the curve means I gave you 2 data points that put me up in this area. Right? And each one causes a different look to the solution. All right. First question. What type of solution do I get if I dissolve 20 grams of KNO3 in 100 grams of water at 90 degrees? So we're using the 100 grams, which means we can look right at the 20. All right, so here's 20, and then I'm going to trace over to 90. All right, so 20, working my way across. Here I am at the 90. So we're talking about this point right here. Then I find my curve. My curve is the KNO3, which is this guy way up here. So if I'm sitting here and the KNO3 is up here, right, at 90 degrees, KNO3 can hold almost 200. grams. I only put 20 in. I'm under that curve. That makes me an unsaturated solution. I absolutely could dump more KNO3 into that water and it would disappear. Question 2. What type of solution do you get when you dissolve 60 grams of KNO3 in 100 grams of water at 39 degrees? So 100 grams means my graph is matching. 60 grams, I find it here. And then I trace over to 39 degrees. Trace over 39 degrees right here under 40. Then I see where I am. Right? KNO3, that's the graph that my cursor is sitting on. So I'm touching that line. If I'm touching the line, I'm on the curve. It's a saturated solution, which means if I drew you a picture, right, it would look clear and colorless. Right? But if I put another grain of solid in, it wouldn't be able to be dissolved because that solution is saturated. It is maxed out. It can't hold any more solid. Question 3. What type of solution do I get if I dissolve 90 grams at those same conditions? So I know 39 degrees puts me here. I trace up the KNO3 at 39 degrees is only able to hold 60 grams. So if I dump 90 grams into it, I am well above the curve. All right. It can hold 60 and I dumped in 90. Right. So what happens? That will create a supersaturated solution. The solution is saturated, the liquid, but I added so much there's leftover solid, 30 grams of it. Why 30? Because at 39 degrees Celsius, KNO3 can hold roughly 60. So if I add 90, it'll dissolve the 60 it's able to, and the 30 that it can't will sit as a solid on the bottom of the beaker. Right, so that's what happens if you land above the curve. Right, the last thing I could ask you is what happens if I change the temperature on you? For instance, what will happen if a saturated solution of NaNO3 is cooled from 55 degrees to 10 degrees? Right, so we find our 55 degrees, and I find the NaNO3. Trace up. Here's the NaNO3. So at 55 degrees, it can hold 120 grams of solid. If I cool that substance to 10, I'm sliding along the temperature axis down here to 10. Well, at 10 degrees, that's above the curve now. It's not touching it like it used to. Right? At 10 degrees, the NaNO3 is only able to hold 80 grams. And if I have a saturated solution, it was maxed out at 120, and I cool it down, now it can only hold 80. What happens is the solid it can't hold falls out of the solution. And it's really cool if you see it happen. You have this beaker that basically looks like it has water in it, and then all of a sudden, out of nowhere, as you cool it off, snowflakes show up in it, right? And more snow, solid, falls out of the solution until you drop back down onto the curve and the solution becomes saturated. All right, so those are the styles of questions you'll see about where you are above, on, or under the curve. All right, last one we could talk about is the direction of the curve, the uphill, downhill. All right, so if an uphill curve indicates endothermic, this is why. Look at your NaNO3. As I increase the temp, it can dissolve more and more solid. That means heat lives on the left side of his dissolving equation. That's why it's endothermic. The downhill ones are exothermic, right? Because they do the exact opposite. I add heat and they become less soluble. It shifts them to the reactant side. Right? So there are many more uphill curves than downhill. Most dissolvings if it's a solid in the liquid, or endothermic in nature. All right, but not all. All right, so I would ask, which of the following have endothermic heats of solution? You could list any of the uphill ones: Ki, NaNO3, KNO3, NH4Cl, KCl, NaCl, or KClO3. Any one of those is gradually working its way uphill. That indicates that it is endothermic. Similarly, I could say, which of the following, and I apologize, that's a typo, which I will fix when I send it. I should say, which of the following have exothermic heats of solution? Right? And if it's an exothermic heat of solution, I'm looking for a downhill, which are fewer and far between. The ammonia, the NH3, it goes downhill. It's exothermic. And the cerium sulfate has a downhill. We would believe that to be or exothermic as well. So that's pretty much it in terms of what we needed to talk about to round out what we know about solutions. Now you understand how heat's a factor and how that links to temp, and we can have solubility curves for them. Right? Homework assignment will be coming to you from Parent Square. It's page 420, number 5 through 9. At 1 o'clock, I will jump on for any questions that people might be having. There's some solubility curve stuff in there. So if you're having trouble reading the solubility curve or understanding any of that, jump on and feel free to ask. Other than that, make sure everybody is coming off a good Mother's Day. And I look forward to seeing you guys soon.